All right, hi, welcome to, this is our, I think, part 4 of 4.2, where we're talking about projections on the lines and subspaces. My plan for this video is to go ahead and knock out projections onto a subspace in one video, just to go ahead and be done and close out our look at 4.2. But you'll kind of see I've got some stuff on the board. To do that, I want to kind of talk general concept and then jump right into the example once we've identified our new set of equations to really set up our procedure to find the projection matrix onto a subspace in particular. When I do that example, I just want to make sure the video doesn't get too long. So we'll see where this ends up, and I may cut this into 2 parts, but we'll see by the end of it. And I've already talked for like 3 minutes anyway. So in this setup, because we're looking at projections onto a subspace, we can kind of view our work in the previous 3 parts as really just the simplest or trivial case for our study here, where instead of having multiple vectors, in this case n vectors, the previous were letting n be equal to 1, and we were only focusing on one vector A that's being projected onto another vector B. So what's different now is that we want to start with n vectors that we're going to assume are linearly independent. So we are going to assume that piece up front. And I want to figure out the answer to this problem. I want to find the combination of these n vectors that are closest to a given vector B. In other words, I want to project this onto B and then ultimately onto any subspace in general. And figuring out what that subspace ultimately looks like. Now, i.e., the way to represent this question is essentially as the linear combination of these vectors, where I have x1 hat a1 plus x hat 2 a2 all the way down to xn hat an. In short, when we find this answer, this vector that's being created here, I want you to kind of notice that this is the same thing as taking our n independent vectors and making them the columns of the matrix A, and doing A times x hat, where x hat contains all of these scalars for the combination. So ultimately our goal is to solve for x hat. We need to solve this problem, but we don't know what P is. And so we got to figure out a way to figure out what x hat is. And then once we know x hat, we can solve for P. We can find our projection specifically onto our given vector. And then from there, just like what we did when we had n was equal to 1, we'll be able to find our projection matrix that can project any vector over we can project onto any vector that we want to from this subspace. Just be careful with my words. So this is our problem. Now I'm going to go ahead and erase this so we can have a little bit of space. There's a lot of work that's essentially listed. Now he kind of goes back and forth between the general case when n is equal to 1 and then extending that just to kind of give a juxtaposition so you can kind of see the procedures and how they're really kind of the same. We're just dealing with different dimensions now that we're kind of increasing to a subspace, excuse me. I'm not going to jump in and repeat everything he says, so if you have the text, then I would follow that. If you have my notes follow the text. And so just know you have that available if you're taking the online class. So what we're going to do is rely on the geometry. Just like when we were looking at one vector being projected onto another, because we're looking for the closest point for that projection, we're essentially looking at an error vector that's perpendicular to my subspace, this A1, A2, AN. In other words, if we take B and I subtract AX hat, this is E. Remember, this was creating our essentially our error vector that takes us from B onto our subspace, projecting B onto our subspace. And we know that this, again, has to be perpendicular. And when our dimension was 1, it had to be perpendicular to A. But now, this has to be perpendicular to every vector, because we need to be perpendicular to the space. And so what that means is that if I take this, if I dot it with every single vector here, so A1 transpose, this should be equal to 0. A2 transpose times this has to be equal to 0. And this process has to be true all the way down to AN transpose. Again, all we're doing is looking at the dot products. These have to be orthogonal, right, in terms of the projection. We think about all the right angles. Essentially, the concept again is that when I'm projecting B onto the subspace, we're creating an E that is at a right angle to every single one of these vectors. So we have n right angles that are essentially created here, and this has to hold true. But when I'm looking at this, notice another way that we can kind of think about this process is that this is just taking these rows now and multiplying it with this. I can represent it in terms of a multiplication of A transpose times B minus A x hat. This has to be true. This A transpose, these rows here, it's just this. We're essentially solving n equations and trying to figure out when they're equal to 0. Because remember, this is just a vector. We're solving a system. And really how we solve x hat stems from this. And then from this, we'll be able to discover what P is and find an expression for that. And so the first step is just to notice the distribution. A transpose B minus A transpose A x hat is equal to 0. By adding A transpose A x hat over, we get this, and I'm just going to write it in terms of this being on the left side of the equal sign. We have this really important equation. Hopefully this isn't too low on the board for the video. We have this really, really important equation because A transpose A, this is going to be a square matrix because if A is rectangular, if it's m by n, then doing this multiplication creates an n by n matrix. So this is square. X hat again is what we're solving for. And A transpose B, this is a vector that we now know. I can solve this for x hat. We're just trying to solve a system of equations now. And this is actually and ultimately how we find x hat. So in terms of our equations and procedure, by using the orthogonality and the geometry, we kind of see first off this important equation that A transpose A x hat has to be equal to A transpose B. But better yet, we see that x hat has to be A transpose A inverse A transpose B. In other words, if I take the inverse of this matrix, because it's a matrix, if I multiply this on the left-hand side by the inverse, these two things would cancel, and I have A transpose A inverse on the left side of A transpose B. Very, very wordy, but hopefully you can kind of follow that structure. But we can find x hat now. If that's x hat, then we know what our projection is, specifically the projection from B onto the subspace. P would be equal to A times x hat, which is AT A inverse AT B, just to be lazy, instead of saying transpose the whole time. So we have this now for when we're going onto a subspace, and I have n vectors for A. And so then the question is okay, well, what's the projection matrix? And the projection matrix is actually seen immediately here because B is already written on the right-hand side. We have that my projection matrix to project any vector B onto the subspace. It's this piece right here. A transpose A, inverse, A transpose. This gives me my projection matrix. So now we can project any vector that we want onto this subspace. And so when we're trying to solve problems and do this projections, these are the three things that we are going to do and follow. We're going to first find our x hat by finding our A transpose A, finding that square matrix, and then ultimately finding its inverse, and then going through and then doing A transpose times B. That'll do that there. We can also think about it in terms of just solving the system here. A transpose B is a vector. This is a square matrix. It represents the coefficients for our systems of equations. And so I'm actually going to solve it that way to find x instead of going this approach. That way we don't have to find an inverse. And then down here, when we're going through and saying, okay, let's find P now, we can put all this together. If I know x hat, we can immediately find P by doing A times that. But we could also do this process here if we needed to. And then go through, we can find P ultimately here, which is how we'll kind of put it all together. Now, a couple things that I also want to point out that he points out, which I think is really important. Two things, sorry to keep turning my back, is one, our subspace, the column space, C of A, is the column space of A. And if you remember when we were looking at A transpose B minus AX hat, how this has to be equal to 0, this gives us, again, that equation up there. Notice how this resembles A transpose Y is equal to 0. This is the left null space. And if you remember the orthogonality of our subspaces, the left null space and the column space are orthogonal to one another. They're connected that way, and we see that here. So linear algebra, we had already kind of established this relationship without even thinking about forming right triangles and right angles, and thinking about all of these vectors in a subspace and trying to find my E from that. We see it really cleanly here, which is really beautiful. So I don't think this has been too long of a video, so I'm going to go ahead and do the example now so we can kind of see how all of these pieces come together. Now, the example's worked out in the text. It's worked out in my notes, but sometimes just verbally talking through it can be kind of helpful. So I will write down the problem but not look at the work, and hopefully you'll kind of see my mentality and I don't make any mistakes. But if I do, oh well. So we have a matrix A. This is going to contain my linearly independent vectors. We're only going to have two here. So 1, 1, 1 and 0, 2, 1, 2. Here are my two vectors. So we have two A column vectors, so we're going to form a matrix here for A. Now the vector we want to project onto the space is 6, 0, 0. So we want to project this onto this subspace. Essentially, we're projecting it onto the column space. To do that, we need to first find x hat. I need to figure out what is the combination that puts us to the closest point in the subspace from B. And so to do that, we're going to solve this system. So to solve this system, I need to first figure out what is ATA. So what's A transpose times A? So I'm going to take my matrix A and transpose it first. So 1, 1, 1, 0, 1, 2. And I'm going to multiply this again with 1, 1, 1, 0, 1, 2. Notice how this is a 2 by 3 and a 3 by 2. So for my people that are still kind of working on matrix multiplication, the result here is going to be a 2 by 2 matrix. We're not going to be left with a 3 by 3, but we're going to have a 2 by 2. And so multiplying this together, row by column, 1 plus 1 plus 1, so 3. Here, 0, 1 plus 2, so 3. Down here, 0, 1, and then 2. Notice how that entry is the same. And then here, 0, 1, and 4, so 5. Notice how, again, we have a square matrix. It's n by n. This matrix is symmetric. This matrix would be invertible, which is really interesting, as long as certain cases arise. And we'll talk about that a little bit more in a minute. But just kind of notice that. And that's really important because if I was to solve for x hat, this has to be invertible. So that's our first part. Now we also need to know what is A transpose B. So I'm going to take my A transpose, which I have on the line above, and I'm going to multiply that with our B, so 6, 0, 0. And again, notice all this is doing is taking the entries and combining them. So 6 plus a bunch of zeros is 6. Zeros out, zeros out, zeros out. Again, notice 2 by 3, 3 by 1, we're left with a 2 by 1. So it looks like this was going to cause issues if you were looking at it and being like, well, how is that going to compare because the dimensions don't match. Remember that we're doing A transpose B. And then x hat would represent the coefficients on this system, or the coefficients. X hat would represent the solution to this system. I apologize, I'm not trying to go too fast, but also not too slow. This is the coefficient matrix to my system, and so I can solve for it now. X1, X2 would represent the coefficients of these vectors for my projection. So when I solve this system, I can create an augmented matrix and solve. So I'm going to go through and do that. Being 2 by 2 should be pretty quick to solve. Let's play some fun music. To solve this, again, I'm going to go 3, 3, 3, 5, augment, 6 and 0. Really quick, row 2 minus row 1. So 3 minus 3, 5 minus 3, 0 minus 6. And then immediately, I'm just going to go ahead and read off my solution. X2 has to be negative 3. And if I plug that in, 3x1 hat minus 9 has to be equal to 6. So 3x1 hat is equal to 15. X1 hat is equal to 5. And checking the book and checking our work, we have x hat matches. We have solved for our first piece of information that we need. There's my x hat. If I know x hat, we know our projection. I can take A and just multiply it with x hat. So I'm going to go through and do that. Let's see if there's anything else. Projection into the column space. Yep, so let's go through and do that. And I'm going to write it out 2 different ways. Really, they're the same way. Just 2 different ways of viewing it. If that's my x hat, remember we find P by doing A times x hat. And this has to be orthogonal to B. Or orthogonal to A, excuse me. Or no, never mind, don't worry about that. Cross that out. I'm thinking of something else. So if I multiply this out, this is going to find the combinations for the point that's closest to B, and that is orthogonal. And so if I do this multiplication, this matrix times this column, 1, 1, 1, 0, 1, 2, times the vector 5, negative 3. I want you to remember that when we're looking at this, this is actually giving you the combination of the vectors themselves. Remember, x1 hat times a1 plus x2 hat times a2, it's finding the combination, it's answering that question, right? What is the combination of these vectors that gets me closest to B? We found that combination now. It's specifically, we need 5 of the first column, and then we need to subtract 3 of the second. And if I do this combination, well, I have 5 minus 0, which is 5, 5 minus 3, which is 2, and then 5 minus 6, which is negative 1. Here's our projection specifically for that B. And so we have it in terms of our combinations. This vector that we have, which is P, we can now find E, that error, the piece that's actually the perpendicular, by going through and doing B minus P. So if I take B, which remember was 6, 0, 0, and I subtract the answer we got, 5, 2, negative 1, this is going to find our error, excuse me, which is 1, negative 2, positive 1. And there's our error. That's our vector that's perpendicular to our subspace, 1, negative 2, 1. This is in the left null space. That's what we've essentially determined from that. From here, if we want to find our projection matrix, we're looking here and trying to figure out, okay, what is A transpose A inverse? Like, we'll need to find the invertible matrix for that. And so let's go through and do that. And so let's find our projection so we can project any vector onto our subspace. So notice again for that, we have everything we need. Again, ATA, we had that done already, so I'm going to refer back to our solution for that, 3, 3, 3, and 5. If I remember right, it was positive 5, correct? Yep. And so if I want to find this inverse for a 2 by 2, we need the determinant. The determinant for this, for A transpose A, is 3 times 5 minus 3 times 3 is 6. And the inverse for this is going to be 1 over our determinant where we now swap the diagonal and negate in the other direction. So here's our inverse for our 2 by 2. And so now if I take my matrix A I multiply it with our inverse, and then multiply it by A transpose, we're going to create our projection matrix, P. I'm going to be lazy, I think, to keep the video kind of short, and so instead of showing all of that multiplication, I'm going to leave that as an exercise, taking this and multiplying it. I do believe I have the work in my notes, so if you're on the online class, you should be able to find my notes, and you can see my work step by step if you need it. Otherwise, you actually see the answer in line 11 on page 156. And again, remember that this projection, if we were to do P squared, if you apply the projection again, it's just keeping you on as the same, so it wouldn't change. Now, one of the things that's really important is when you're looking at this answer here, you need to be really careful about applying A inverse and distributing that to both A transpose and A. Because if we were to kind of follow that idea, it looks like everything's going to cancel out, and our projection matrix would just be the identity matrix. But we have to be very, very careful because A could be a rectangular matrix. So then if we apply A inverse, A transpose inverse, like if we apply this property, this may not exist. If the matrix A is rectangular, this doesn't exist. Or rectangular matrices aren't invertible. So that's why we need A transpose A, why that's so important, is because if A has those linearly independent columns and I do A transpose A, we're creating a symmetric, linearly independent, invertible matrix, and that this is then solvable. We can go through and find that projection. It all stemmed from the premise that these have to be linearly independent to create that kind of result. And so again, what this is, the whole purpose of this video, just to kind of wrap this up in terms of a brief summary, and he gets into the brief summary at the bottom, is we were trying to project a vector onto a subspace, onto the column space in this case. And when we do that, we're trying to figure out ultimately how far away is this vector from this subspace. What is that shortest path to get to that vector? And in order to do that, we first have to figure out what are the combinations of these vectors that gets me in terms of the closest point to B. That point has to be orthogonal. So we used the orthogonal, which is the left null space, to do that. If we're looking at this again as the column space. From there, we can find our projection, which would help solve for E. We can find then that error vector that takes us from our subspace into to where our vector B is. And then from there, we're able to calculate our projection matrix, which can now project any vector we want in n-dimensional space into our subspace of A1, A2, AN, our matrix A there. And that rounds us out for 4.2. As far as the online class currently for the year 2026, we are not going to look at least squares, but you'll see that in terms of the notes. If you want to see an application of all of this, like why is this so important? How does this play a role? And then we're going to move straight into the Graham-Schmidt process, because this is one of the greatest kind of theorems that's used later on, as well as an algorithm, and really a huge application to orthogonal bases and how to factor a matrix into a better and kind of unique way than what we've seen so far. So if you have any questions, please let me know. Otherwise, this video's done.